Hi, I'm Jack Waudby, and this talk is about preserving reciprocal consistency in distributed graph databases. This work is the joint effort of Paul Ezhilchelvan, Mitrani, and I at Newcastle University, and Jim Webber from Neo4j. Graph databases model data as a property graph, with vertices representing entities and edges capturing relationships between entities. In addition, vertices and edges can have a number of associated properties. In this model, edges always have direction. As can be seen in this simple graph, Tolkien wrote The Hobbit. However, in the storage layer, this edge directionality does not exist. Both vertices and edge connects store information about the edge. This can be seen in the storage layer representation of Tolkien wrote The Hobbit in Figure 2. In this representation, database records consist of a sequence of properties and an adjacency list. Both adjacency lists of the vertex Tolkien and the vertex The Hobbit contain reciprocal edge pointers for the edge rows. This improves query performance as it allows edges to be traversed in both directions. When the pointers for a given edge refer to each other in such a complementary manner, that edge is said to be reciprocally consistent. Ensuring reciprocal consistency for edges in a distributed graph database is important and challenging. Graphs can seldom be partitioned into disjoint sets. A common approach to partitioning is to use a balanced edge cut, where vertices are evenly assigned to partitions in a manner that minimizes the number of edges that span partitions. Such edges are known as distributed edges, as shown in Figure 3 with dashed lines. In practice, anywhere between 10 to 30% of edges are distributed edges. For such distributed edges, a degree of concurrency control across partitions is needed. Else the edge can easily become reciprocally inconsistent, which can have a serious impact on the usability of the database. Let's take our running example, Tolkien wrote The Hobbit, and assume it is a distributed edge spanning servers I and j. Now we have two concurrent transactions, x and y. Transaction x deletes the wrote edge, and transaction y appends a property year to the edge. The order in which a transaction updates the reciprocal pointers of an edge is unconstrained. Therefore, it is possible that transaction X updates its first edge pointer at server I, and transaction Y updates its first edge pointer at server J, making the following interleaving possible, which leaves the edge in a reciprocally inconsistent state, where a subsequent read of the edge from server I returns a different result than reading from server J. In the storage layer, there are now two inconsistent unidirectional edge pointers, as can be seen in Figure 6. The problem with reciprocally inconsistent edges is that they are a source for semantic corruption. Semantic corruption occurs when a subsequent transaction reads an inconsistent edge and performs a write based on this read, with further semantic corruption spreading by the same mechanism. Many railway graphs are scale-free. That is, their degree distribution follows a power law. Because of this, semantic corruption spreads alarmingly fast. Therefore, it is imperative that reciprocal consistency is preserved to prevent this phenomenon. To preserve reciprocal consistency, one can implement serializable distributed transactions at a cost to performance. However, we opted for a different approach, designing a lightweight concurrency control protocol that aimed at just preserving reciprocal consistency for distributed edges, a much weaker guarantee. When designing this protocol, it was important to consider the defining characteristics of graph databases. Firstly, graph workloads tend to exhibit high contention, again a result of many graphs' scale-free nature. Secondly, graph transactions tend to be longer lived than those in other databases. Therefore, the protocol must permit multiple updates on the same distributed edge, provided they are sufficiently apart in time to ensure reciprocal consistency. What we developed was the Delta protocol, which makes use of the fact that when updating a distributed edge, a transaction must update one edge pointer, then immediately update the other. We introduced a simple rule, where a given update on an edge pointer is permitted if the immediately preceding update was done at least delta time before, else the transaction is aborted. This is based on the assumption that when updating a distributed edge, the time that elapses between completing an update on the first edge pointer, traversing the network, and starting at the other edge pointer can be estimated to be some value lowercase delta. In a practical setup, to obtain lowercase delta, we are required to make a best effort estimate on the upper bound on the delay between database servers. This then allows us to set meaningful values of capital delta. Let's look at an execution of the protocol. In this example, thick black lines represent the parameter capital delta, which we assume has been obtained by estimating the network delay between servers I and J as described in the previous slide. Transaction X starts at server I and begins traversing the network to server J. Transaction Y starts at server J and begins traversing the network to server I. When transaction X arrives at server J, transaction Y's update is within delta, so transaction X is aborted. When transaction Y arrives at server I, there is no update within. When transaction Y arrives at server I, there is no update within delta, and therefore transaction Y succeeds. In this execution, reciprocal consistency has been preserved. We can say reciprocal consistency is preserved if the time taken to complete an update at one edge pointer and start at the other remains less than delta. However, there is the possibility that delta is exceeded and the edge becomes reciprocally inconsistent. Semantic corruption can then occur and spread as before. Let's look at an execution where this can happen. Transaction X starts at server I and begins traversing the network to server J. Transaction Y then starts at server J and begins traversing the network to server I. Transaction Y arrives at server I, and when it gets there, it sees no update within delta from its perspective, and therefore it succeeds. This same happens with transaction X when it arrives at server J. In this execution, reciprocal consistency has not been preserved. This leaves us with a trade-off between the size of delta, the occurrence of reciprocally inconsistent edges, and hence the spread of semantic corruption, and the number of aborted transactions. The larger delta, the less likely a distributed edge becomes reciprocally inconsistent. The larger delta, the less likely a distributed edge becomes reciprocally inconsistent, but this comes at the cost of a possibly more aborted transactions. We evaluated this trade-off through simulations for various values of delta. Specifically, we looked at the time taken until 10% of edges in a large distributed graph database consisting of 11 billion edges became semantically corrupted, and the fraction of aborts per second for varying transaction arrival rates. To be conservative, we chose 3 large values of delta. This first chart plots various transaction arrival rates against the time until 10% of edges in the graph database are in a semantically corrupt state. Without any concurrency control, the time until semantic corruption is between 50 and 499 days. Setting delta equal to 50 milliseconds significantly increases the time until corruption to between 317 and over 27,000 days. Setting it to 75 milliseconds increases it even further to between 22,000 and 1 million years. This next chart plots the fraction of aborts against the transaction arrival rate. When we set delta to 50 milliseconds, the fraction of aborts is between 1 to 5%. This increases to between 1 and 7% when we set delta to be 75 milliseconds. In summary, to summarize, a lack of concurrency control in distributed graph databases can lead to reciprocally inconsistent distributed edges. This can then result in the spread of semantic corruption. The delta protocol prevents reciprocal inconsistency given some value delta is not exceeded. The delta protocol significantly reduces the spread of semantic corruption to the point where it's no longer a concern at the cost of a very small fraction of aborts. Thanks for listening.